Swayam Prabha. Digital India. Educated India.
So this is the definition that we saw in the morning about what an IoT is. What is IoT? It describes a network of physical objects, which are sensors, actuators, the same good old things, I think, which we are all aware of. But we bundle them all together and call them things. And they communicate by using some layer of internet protocol or the other. As I told you, it need not be internet as we see it, but it could be any of the layers of internet communication protocol. And because they communicate that way and they are all things and they communicate using internet, it's called Internet of Things. They basically connected, they exchange data, and then there is a lot of interesting things that you can do with that. And we said consumer applications, healthcare, manufacturing, agriculture, environment monitoring, military, things like that. So before I move on, have any of you encountered an interesting IoT application? And do you want to take a few seconds to talk about it? This is an open-ended talk. This because we know a little bit about embedded systems and cyber physical systems and IoT. I just wanted to know specifically, have any of you used or developed or worked with an IoT application? And do you want to take a few minutes to talk about it? You could just unmute and talk. I am not sure if I heard what you said fully, but I did hear that you worked with Alexa before. So I hope others are comfortable with what Alexa is. It's Amazon's personal assistant, it's like a little blob that you can get. And there are lots of jokes about it if you don't like Alexa, but if you enjoy Alexa, Alexa can become a good friend of yours. You can just Google for it or Amazon for it. Anybody else has used IoT? When you all filled up forms, some of you had given very interesting examples of I did this and that. So it'll be good to hear some stories.
Ma'am, actually, I work
Relaunch,
with
okay. Yeah.
IoT. I don't know exactly it would be IoT device or not. I have programmed a rain sensor using Raspberry Pi.
Okay, okay. So using REST API, you say, Sushmita. Yeah. So that's as good as IoT. Anybody else?
Ma'am, I did a mini project on greenhouse control and monitoring system using IoT. So
Okay.
basically, what we did was we monitored certain characteristics like soil moisture and light and humidity, and then we controlled it using the actuators and sensors, and we fed the data to the website. So using a Wi-Fi module, and yeah, that was the brief about the project.
Yeah, so that's an excellent example of a IoT application in the field of agriculture, maybe agriculture and
Yeah.
farming, basically. Yeah, okay, good example. Anybody else? Even if you're
Ma'am,
not
I'm
worked,
Ashwini.
you've used. Yeah.
I did a project on IoT based water monitoring and controlling using Node MCU flow sensor and motor and motor driver. So basically, it's the same mechanism as how we used to close the taps manually. The same methodology is used here, which is achieved by a DC motor. So, for example, in horses and in big crowd areas and all, we cannot ask people to use water efficiently or not to waste water. So, for that purpose, we devised this project so that we can automatically do this controlling of flow water in our Android app itself. So we basically used the flow meter to sense the data of flow of water to first of all know the water usage of people. So according to that, we can reduce the flow water So that sensor data is sent to the cloud, and then we plotted a graph for daily usage of water for whatever field we are using it for, and in that way we did, ma'am.
Yeah, I think this is another excellent example. So glad to know. Thanks, Varshini. Anybody else? Has anybody observed IoT system working as a part of your workplace, or while you're parking your car, or in any other city? Have you seen something that you think made you think, oh, is this an IoT? Things like that. Any experiences like that? In Bangalore, where I live, we have a pay and park system, and that's a classical IoT system. And I can pay either by using a cash from the parking console they have, or I can have an app in my phone and I can pay, and I choose the parking slot. There's a sensor that reserves the parking slot for me for the car that I have for so many hours. It gives a warning 10 minutes before my parking expires, saying that you better renew it, because otherwise you'll have to pay a heavy fine, and so on. So this is another IoT system. So it's a very evolving area. So as always, Gartner is a technology company. So like we saw Gartner's hype cycle for embedded systems, what is Gartner's hype cycle for IoT? I'm sorry about the clarity in the image, because this was an image taken from a Gartner report, but I hope you can see it clearly. So it's the same thing. Hype cycle means what? People imagine that IoT will go somewhere. But what is the reality? Which are the technologies that are ready to take off in less than 2 years? I mean, which will settle down? Which are the technologies that will take 2 to 5 years to settle down, 5 to 10 years, more than 10 years, and which are the technologies that are going to be obsolete? So if you see here, and you see the legend below here: white circle, blue circle, dark blue circle, yellow triangle, red cross, and a circle. There is no technology in IoT that's going to become obsolete. That's what Gartner is saying. All IoT technologies are meant to rule us, rule our world, and rule our development. So it's a wonderful technology area to be in, to develop expertise in. And which are the technologies that are going to see a plateau? IoT integration is already going to see a plateau. And where are we in terms of peaks? These are all the things: edge, IoT enabled application, blockchain and IoT, then IoT security, IoT in services, healthcare, indoor location, digital business. Autonomous vehicle is the only thing which says Gartner is going to take more than 10 years, because an autonomous vehicle to go in roads, forget about Indian roads, even to go in roads abroad is going to take really, really long time. But otherwise, as per this graph, IoT is a technology that is set to take off and be a very dominating class of technologies for the near future. So this is the emerging IT scene. This is IoT is a place where embedded systems, electronics, electrical application, everything merges with information technology. Again, this is a hazy picture, but I'm sure you can make out these sensors, right? The digital watches, Fitbits, you have cameras, you have swarm robots, you have TV, you have your computer and phones and whatnot, and everything is slowly going to go. And where is the core infrastructure going to be? It's going to be on the cloud. Right. So this is the emerging IT scene, and this is how it is going to look like for a really, really long time to come. So we all know this. Application areas can be found in several areas. We are literally surrounded by it, whether we like it or not. Some way or the other, IoT is going to influence us. If you live in a remote, in a village or a smaller town, IoT is present because there's agriculture use of IoT. If you live in a big city, then IoT is present because traffic, parking, and other things are managed. Of course, you could create IoT in your own life by using Alexa and a few other things. You could make your house smarter, you could make your cities smarter, grids, you could make your industry smarter. A lot of things are being done there. Healthcare, IoT is present. Smart retail, this COVID is the talk of the community, right? As far as healthcare is concerned, I got vaccinated, my husband got vaccinated, so we have that app, COVID app portal. We register to that. Immediately one message comes into my phone, And the minute the vaccine was given, literally the minute the vaccine was given, I got another message. So this is another literally IoT application, right? The nurse presses a button in the device that she has after giving the vaccine, and I get a message. So it's extensively used everywhere. Smart retail, supply chain, wearable technology, you name it, IoT is used. So I'll talk about a bit about the theory of IoT. As I told you, you have plenty of opportunity to learn the practical aspects over the coming few days. So this is based on a study that Nagalakshmi and I did for when she started on her PhD work. Her PhD work is on the verification of IoT systems, applying formal methods for IoT applications. So we wrote a sort of a study report when we read up about it, and a lot of this presentation is regarding that study report. So IoT application is not one for all. Like the few examples that you gave you, right? Some of you worked with Alexa, some of you worked to develop water saving mechanisms, some of you worked to help in the context of agriculture. Each one is heavily custom built. You cannot say that, oh, I learned this, and so because I learned this, I can do something else that easily. You'll have to literally start all over again. It heavily depends. It's not a one model for all kind of thing. It heavily depends on the type of IoT application. A shallow IoT application can have just 3 layers of architecture, or a detailed one, as you see on the right, can be a 5-layered architecture. So let's spend a little bit of time understanding this picture that we have on the right. So if you see the bottommost rectangle in the picture, that's what we call a perception layer, which means there are physical objects which we know reasonably well about, all kinds of sensors, all kinds of actuators, RFID tag. My phone can act as a sensor, Fitbit can act as a sensor, anything can act as a sensor. So a perception layer basically deals with physical objects, what exists, what can talk to each other, what is their kind, how long can they survive, what kind of backup support do they need, what kind of battery do they need, how do I read data from them, how do I give back data to them, and things like that. So that's the perception layer, the building blocks. And then comes the transmission layer, where the data that is collected or read by these physical objects is transmitted up and above for the application to process it. So a transmission layer is where information transmission happens. It could be a network within your home, like Alexa. It could be a field area network. It could be a wide area network. It could be through internet. It could be through a lower level internet protocol, almost anything. Middleware layer is where you do the backup. Like, for example, Nagalakshmi will tell you a little more tomorrow. The way AWS works is that the first thing it will do is, for every data that you'll send, for every device data that it will send, it will create a shadow. What it means by a shadow is that it will create a backup, like a sort of backup of that data, so that even if the device goes out of power or out of battery, it has data to work with. And while creating a backup, it will secure that data so that nobody can tap into it, and it will move on like that. So, and then if needed, it will store it onto a database, and then it can make some decisions. It can do a lot of things there. So that's where all this cloud, ubiquitous database, decision making, things like that come. Please remember that in a hardcore cyber physical system or in an embedded system, you almost will not find these kinds of things. There will be decision making for sure, because you're doing some control or some control algorithm, but you almost always will not have access to cloud, at least during the run. You may not do an extensive database. You'll have sensor data, but you won't call it a database. In an IoT, you can collect sensor data and create database out of it, and then call it big data and do whatever you want. Those kinds of things may not exist in cyber physical systems. When you start doing these things, the cyber physical system becomes what we call an IoT. And after that comes the application layer, where actually the smartness or the real functionality of the IoT comes into picture. So, okay, you have read these data, you've passed them across networks, and then you've created backups, you've done some processing and stuff like that. What are you going to do? You're going to make things decide smartly, make them behave better, make them do things like, for example, Varshini said is a very valid case, right? If you're in a hostel or you're in a hotel, the last thing you're worried about is to save water. You'll open the tap, you'll talk to your friend, and then wash hands and hold your hands, talk to your friend, won't worry about closing the tap. So it's a complete waste of water. So I want to make the solution smarter by regulating the amount of water that flows into it. It's a tough application to work on and design, but I can do it because I have the ability of an IoT application to do it. So those things will sit here. And finally, business layer. Business layer is not meant for everybody. Like, for example, for the kind of projects that were described here, business layer does not exist because you develop this project as a part of your academic learning environment, and you did it for whatever reasons. It could be because of your course credits, it could be because of your term project, it could be because you wanted to develop expertise, build your CV, whatever reasons. But you're not going to go ahead and sell your product. You're not going to say, this is, see, by doing this project, I figured out a niche way of developing this kind of applications. So I want to, tell you how to develop these kinds of applications. You're not going to be able to do all that. So when you do all that, like Amazon Web Services is doing, then you have a business layer on top of it. Business layer is when you begin to offer it either for free or for a price to people. So this is the 5-layer architecture. So this is how IoT applications work. So the basic 3 layers that are all present in all the applications, you could do it as a classroom project or you could do it big way. You have to read data from objects, you have to send it across a network, and you have to do some processing. There is no doubt about it. These 3 you'll have to do for sure. So perception layer is a collection of sensors, actuators, or things that have to be connected, and it is responsible for gathering data from things. And the biggest challenge to address here is, am I gathering the right kind of data? Am I gathering it at the desired accuracy level? Next comes the transport layer or the network layer. This manages secure data transfer and processing, where several IoT specific protocols are used and developed to cater to IoT application. I'm presuming Professor Sudeep Mishra will talk a little more about it. Professor Das on the last day will also talk about it. We will talk to you about IoT protocols. I will give you a list of them: MQTT, XMPP, AMQP, things like that. So those are things that help data read from the sensors to, save them, protect them, make sure the shadows are created and so on, and send it up. And you have to do it in such a way that no data is lost, communication is reliable, and at the same time, you don't retransmit again and again to ensure that communication is reliable. Then comes application layer, provides the main functionality to deliver the application that is being developed, and it is heavily context dependent, as we saw. So in this 5-layer architecture, 3 layers are almost always mandatory: perception, transmission, and application. Middleware layer if you want very rich functionality, otherwise it can merge with the application layer, and business layer only if you're running a business out of an IoT model. So these are the additional layers. Middleware layer is the real differentiator of IoT from embedded and cyber physical systems. That's what I told you, right? It supports cloud computing, analytics. Of course, even in cyber physical system, you can do image and signal processing. You can store data and all that. But if you want to do it the true internet way, then IoT, a cyber physical system becomes an IoT system. And because of this, that IoT caters to several different application areas, literally several different application areas, like smart homes, Alexa, and things like that. They're traditionally not cyber physical, right? Whereas if you see smart industry, maybe it existed even before. Next is business layer. Business layer adds further intelligence, as I said, helping firms to sell their IoT product and maintain it. Large corporate companies like Amazon and others use business layer extensively, make parts of it open source. As I told you, AWS IoT, which you will learn about, has several free tier applications, uses an extensive business layer model. And when I look at architecture and try to categorize into 2 categories, I can classify them based on where the data is processed. It can be processed in the cloud, or it can be processed in what we call the fog or an edge. So if you go back here, data is read at the perception layer in IoT from things and processed, and transmitted using the transmission layer. So based on whether you differentiate between the middleware and application or you merge them into one, you could classify architectures into two kinds. One is you call it cloud based architecture. This supports centralized processing of data. All the applications are deployed on the cloud. Complete processing is handled by the cloud. This is useful to handle large volumes of data, support analytics, and it is supposed to make the IoT devices and the applications smarter. Disadvantage is that everything has to go to the cloud all the way and then come back to the data. There are no intermediate storage points, intermediate retrieval points. So it results sometimes in communication overhead due to excessive transmission of data from devices to cloud. The other is you have devices along the way. So in IoT, we have names for them. They are called edge devices, aggregator devices, and the computing that you do with them is called edge computing and fog computing. Professor Deepak Gangadharan, next week, Tuesday, will talk to you about detail in about edge and fog computing. So here what happens is that you don't send everything to the main cloud or the main computer server. There are intermediate devices where you can keep data and then move on with it. Let me give you an example. I told you, right? Like in Bangalore, certain parts of Bangalore, we have a smart parking system where you'll have slots. You go and park your car in that slot, and it's a large road. At two ends of the road, there will be these parking meters. So you have to go to that meter yourself. You have to remember the slot. There'll be a 3-digit number with a sensor on that slot. So I parked my car in slot number 558. I go there, I type slot 558, then I choose 1 hour, 2 hours, 3 hours of parking, and then I can pay by credit card, or I can insert cash, or if I have the app, I can do Google Pay, whatever. And then I come back. So this data is stored. And where is it stored? It is stored in that parking meter. It's not sent to Bangalore City Traffic Police cloud computing area, because it's a very temporary data. If suppose I've chosen parking for 2 hours and some reason I'm running out of the parking, and the parking system is so smart, it senses that I have not taken it out, and it will send me an SMS. Suppose I have that app, it will send me an SMS saying that you have 10 minutes before your parking expires. Do you want to come and renew it now? So to do this kind of thing, I do computing on the edge, which is at the parking meter level itself. I may not do anything at the cloud level. So it depends. So this is a classical example of fog or edge-based cloud computing, where I monitor, pre-process, storage, and do security below the transmission layer. Raw data, pre-processed data is sent to the edge nodes. It results in efficient use of data, additional analytics, it saves energy, battery. 5-layer IoT architecture is the base for edge and for fog computing. So let's look at the physical components of IoT. We've seen reasonable detail about sensors. We know what a sensor is. Now, again, repeating the definition. They are the building blocks of an IoT system. They are present at the perception layer in the IoT architecture. Typical IoT sensors are RFID, infrared, GPS, medical devices, chemical sensors, temperature, humidity, pressure, wind, pollutants, noise. I think a lot of you told about all this. In sophisticated IoT system, camera is also a sensor. Your phone can be a sensor. Alexa can be a sensor, and so on. So what are actuators? Again, we know the definition. They are devices that receive control signals and convert them into the required action, motion, or command. Where are they present? They are again present in the perception layer of IoT. They are driven by control signals and the energy source, which is usually some hydraulic or something like that. Utilizing the energy from energy source, an actuator is responsible for making the control signal to act on the environment. It actually does motion, open, close, linear motion, rotational motion, and so on. Typical actuators used in IoTs, all these things: digital MICR, electric motor, hydraulic cylinder, pneumatic actuator, servo, solenoid, stepper motor. Again, we saw a lot of these kinds of examples. Now let's talk about communication. So I'll go back to this figure for a minute. So sensor. Now the crucial thing is communication. In IoT, So in embedded systems, you can communicate by wiring, literally connecting two wires, putting a one HDMI port here, an RS-232 thing here, or a USB there, and things like that. In an IoT, not all communication happens like that by literally stringing together wires. Typically you will find things like, oh, I used my phone to send that data. I gave a command from my phone and I used Alexa to do this, something and all you will say. Or I just got an email, I got a notification. So what happens? How is communication in IoT going to be different from communication elsewhere? So communication in IoT happens in three ways. One is the devices can communicate with each other. The other is it can happen between a device and a cloud, or it can happen between a third party cloud and the cloud where applications are deployed. Let me give you an example of how, or maybe I should ask you, can you think of an example of one small scenario where two devices or things in an IoT communicate with each other? Just some example that you can think of.
Using mobile phone to control TV.
Yeah, using mobile phones to control?
TV, smart TV.
Exactly. Using your mobile phone to control a smart TV. Absolutely. So, a smart TV communicates directly with the mobile phone using Bluetooth or Wi Fi, and then you're done. There is no cloud, no edge, fog, nothing. Right? They just tell each other. Like, for example, I want to I have some music in my phone and I want to connect my phone to my TV, which can read Bluetooth or my Bluetooth speaker, and I just play. So these two talk to each other. They are fine. They nothing, no cloud, no edge, no computing, nothing. So the next is between a device and a cloud. Any example?
In vehicle area networks, the vehicle have to send data so that they can be monitored their health and
Absolutely. Fuel level, speed. Exactly. So the vehicle has to send data. So that is device and the cloud. Fine. Great. And between cloud and cloud, I mean, what I'm saying is, I mean, the third party cloud and cloud. Can you think of any example?
We all use Google Drive. This is
Yeah. So we all use Google. Sorry.
uh, uh, Gmail. The drives of Gmail it is stored in Google Cloud anyway.
Yeah. But in the context of IoT, so that's an example. Absolutely. No doubt about it. In the context of IoT, can you think of a scenario? You will learn it tomorrow morning. AWS will be a whole thing on the cloud only. So that's the third party cloud, and the cloud in which your application will be deployed will be local to it. So that kind of thing also happens. And it happens with a diverse set of protocols, really diverse. And the standard OSI protocols cannot be directly used for IoT device because IoT devices are mobile in nature. They're very resource constrained in terms of energy and memory. And so we have a whole set of robust new protocols that have been specifically designed for IoT. Yeah, so before we move on, does anybody remember any protocol that has been specifically designed for IoT? Have you heard of any term?
Zigbee, LoRaWAN.
Zigbee was designed only for IoT or this exists before itself? Maybe Zigbee was adapted for.
Zigbee was before.
Yeah. Anything very specific to IoT?
AMQP,
Okay, excellent. Any examples like that?
MQTT, ma'am.
MQTT, yeah, excellent. So MQTT and all, I mean, Zigbee is a beautiful example of IoT protocol. It is very well used in IoT, but it wasn't exclusively designed for IoT, whereas MQTT is one. So let's look at communication protocols. You'll learn more about it as we move. All the devices at perception layer has to connect and communicate across the network, right? So RFID, Bluetooth, those are small things that help devices to connect each other. Network protocols help to communicate across the internet, and data transfer protocols help to disseminate data in a secure way. But the problem is each protocol is of a different nature, right? Bluetooth works differently, MQTT works differently, Wi-Fi works differently, and each work at different layers. So there is a lot of interoperability issues that can come up if you use very vendor specific protocols. So usually people fix a protocol stack and then say this is how communication is going to happen and this is what it is, and then they will work with that based on the devices they have and what it is. So here are some popular IoT protocols which we've made an attempt to classify based on the layer in which they are used. So I hope you're comfortable with an application layer, transport layer, network layer, and physical layer, and things like that, right? So at the application layer, we have MQTT, our good old HTTP, because it's internet, HTTP is useful. AMQP, somebody said that. Apparently, as per the Gartner survey, AMQP may not survive. I mean, that's what Gartner predicts. Let's see. Then you have XMPP, SMQT. I mean, don't get put off. There are lots of abbreviations, but each one has a meaning. If you studied even one protocol, you'll understand what it means, right? So MQTT is message queuing telemetry transfer protocol. It has a big standardization body, and then you can go and read that standard. Pages and pages of data will be there. It commits to certain QoS. It works like this, it works like that. Roughly the one that is closest to our SMS, the simple messaging service that we use on the phone, the things that we use to get our OTPs and all, MQTT is that. It's more or less equivalent to that. Similarly, all these protocols exist. In the transport layer, it all becomes TCP/IP TCP or UDP. The network layer, I can use IPv6, 6LoWPAN, whatever I want. And then ZigBee, which was already said, Z-Wave, Wi-Fi, 802.3, wireless LAN, Bluetooth low energy, 2G, 3G, 4G, and so on. Right. So in this, for ordinary data transfer, typically MQTT, COAP, XMPP is also meant for data transfer. HTTP, ZigBee, Bluetooth are meant for as a perception layer for network connection establishment. You know how sensor dies, somebody comes back and puts battery in it or charges. How do you use? Then they have to establish connection by saying request response, publish, subscribe. So they have all these standards. You learn a little more about them in Professor Sudeep Mishra hasn't actually said what he's going to talk about, but I presume he's going to talk about protocols. But Professor Das is definitely going to talk about protocols on the last day. So you will definitely learn there. So that was like a sneak peek into IoT protocols. Of course, you don't get put off by what are all these terms, I don't know, and all that. A lot of IoT development can happen without knowing about them. Even I don't know. As I told you, I'm not a communication engineer, not even an engineer. So we can still develop and do a lot of things about IoT without knowing about the protocols in detail. Then comes operating system, because as this part we didn't discuss in the earlier sessions, but okay, you have sensors, actuators, they're transmitted, then you do some computation. Everything is relying on an operating system, right? So they form another backbone for IoT applications. It has to give you the multiple threads, the processors, this scheduling. It has to do the computation, everything. It needs APIs to handle different aspects of IoT architectures. So IoT applications usually use what we call a real-time operating system, abbreviated as RTOS, real-time operating system, because timing requirements are very critical. Like I told you for this parking meter example, right? Timing requirements is very critical. If it takes 20 minutes to tell me that I have only 10 minutes of parking left, then it's gone. Right. So it has to happen on the right time, sometimes in a fraction of a few milliseconds. So you don't need good old operating systems like Windows and all may not work. You need sophisticated operating systems that are consciously aware of real-time constraints like FreeRTOS, Google Brillo is there. Then there's something called ContikyOS and so on. So many, actually, huge number of operating systems exist. When we did that survey, we found maybe about upwards of 15 different operating systems, almost all of them real-time operating systems that are exclusively used in the context of IoT. What I have shown you here is a small example. Tomorrow, when we work with AWS, you will learn a bit more about the first one, because AWS works over free RTOS, and you will get to know what's happening.
Is RTOS used for embedded systems as well?
Yes.
Okay.
All embedded systems, cyber physical systems, and most of IoT. Of course, Android also is used, and Android is a kind of a real-time operating system. Of course, higher footprint. But embedded systems cannot work without real-time operating systems. These microcontroller operating systems that run on microcontrollers can read embedded devices, small footprint devices. FreeRTOS is a robust open source real-time operating system. There are giant operating systems that people use, like for example, aeroplanes have a time and space partition operating systems that they use. VxWorks, I don't know if you've heard about that. That's a very popular time and space partition operating system that is used by aircrafts. That's also used by PLCs and several different other things. FreeRTOS is one, VxWorks is one, Honeywell has DOS, and so on. Several different operating systems exist. All of them are real time. Another important aspect of IoT is security, because everything is on the internet, everything is going to communicate with everything. Once I heard a talk from an IIT Madras professor, Professor Balram Ravindran, and he doesn't work on IoT, but he works on machine learning and data and all that stuff. So it's a big thing now, no? IoT is one big area. Of course, machine learning and data is another big area. And obviously, machine learning is also used for IoT a lot. So Alexa, for example, if you have it on, it's all the time listening to you, right? Whether you like it or not, is all the time listening to you. Same thing happens in your phone. If you have your location on and if you have your data or Wi-Fi on, Google is literally all the time listening to you. By mistake, suppose I search for something, I don't know, let's say I search for, suppose I want to buy a handbag, and because we have lockdown, and I search for handbag in Google or go to Amazon and search for handbag, after that for a few days, whenever I go back to Google, whichever site I go to on the internet, it's going to bombard me in the side, up, down, everywhere about handbags. Right. So this is a common thing that we would have observed. So this Professor Balram has an Alexa at home because he's a machine learning researcher. And he also apparently learns yoga, he said. And when they were doing yoga, the yoga instructor said something like, take a deep breath and do something and slowly exhale or something like that. And Alexa suddenly let out a message saying, I'm sorry, I can't do that. So what I'm saying is that security is a big issue. If you have these devices on, if you have these entities on, they are basically listening to you, knowing your movements, they know what you're doing. And as youngsters, maybe many of you enjoy it, but very soon you'll realize that this is a breach of security, right? Why should Alexa or Google know where I am? It is going beyond helping me. So IoT security is a very big area, and Mr. Soren from Micron will be doing a session on this. So there are 4 security objectives that an IoT system requires. One is data confidentiality. Unauthorized people cannot have access to the data that is transmitted and stored. Some people cannot tap into it. Like for example, suppose you lock your house and go away for 1 week, and you tell Alexa, you shut yourself out for 1 week, and exactly after, whatever, in volatile, non-volatile way, and exactly after 1 week, you go into the sleep mode, and exactly after 1 week, you wake up and switch on this light because I'm going to come back after my trip or vacation. Right? This data is very confidential because somebody tapping into this will know that your house is going to be locked and they can plan their own burglary or something like that. So data confidentiality is very important. Data integrity is very important. The data that is collected, transmitted, and stored cannot get corrupted, cannot get changed. So that is also important. The next one is non-repudiation. So what it means is that the sender cannot deny having sent a given message till you delete it and things like that. The other is availability of data. When the data is collected, I mean, generated, transmitted, and stored, it should be available to those who are authorized, even with denial of service attacks. So these are four important security objectives, and a lot of work on IoT security goes into designing a system for these kinds of objectives. Next, one of the last things is IoT safety. Several IoT applications are safety critical, right? Because what they do or not do matters a lot. Like, for example, imagine an elderly senior citizen living alone at home, assisted by Alexa or Google Assistant, and the person is on the bed, but he would like his door in a smart home to be opened exactly at 9 a.m. because his attendant is going to come in. Suppose there's a mismatch, there's a compromise on safety. The door instead opens for somebody else, door opens without the person being authorized, door opens at some other time. All these are compromise issues on the safety of an IoT system. Similarly, you can think of an industry control where pressure or temperature data or humidity data is being monitored, and pumps have to be turned on or off, valves have to be turned on or off. If there is a compromise in the safety, or if there's a fault, then the consequences can be disastrous. So verifying for them for safety is a very important problem, and safety is different from security and privacy. So this is also an important issue that people usually worry about when it comes to IoT. So yeah, so tomorrow Nagalakshmi will give you a demo on AWS IoT. The biggest benefit of this is, as somebody rightly asked in the morning session, I am at home, my university is online, my college is online, I want to learn about it. I obviously don't have an Arduino board or a Raspberry Pi, I don't have the sensors, I don't have a development kit. Can I still develop an IoT application in such a way that it is almost ready for physical deployment if and when I go back to the place? So, how do I go about doing it? There are two ways that we will teach you to do it in this summer school. One is using this Arduino programming. Professor Deepak says that he is going to give you a completely virtual simulation environment which will let you program Arduino boards. And the other one is AWS IoT. Similarly, you have Apple also has an offering, Samsung has smart things, Google also has an offering. Most of these large multinational IT firms have their own IoT framework. Some of them are proprietary, which have paid and use. Some of them are free and open source. AWS IoT is partly free, partly proprietary. So it's up to us to use the free part. And for those who can afford to pay for whatever or based on the need, they could go and pay and use the proprietary part. So I will just show you the user interface. So I've just opened this web page from my web browser, right? Just search for AWS IoT in Google. It'll open this web page for you, right? It's Amazon Web Services, and they have a lot of other products, but they have IoT. So AWS IoT are IoT services for industrial, consumer, and commercial applications. There's a nice video here that you can, play and learn about what happens, what does AWS IoT do. But they, like, for example, you can develop an industrial solution. You can develop a connected home, smart home. You can develop a connected city, a smart city. It will give you interfaces for developing all these kinds of IoT application. It works on FreeRTOS, which is an open source operating system for microcontrollers. It has something called Greengrass, which is an Amazon software that lets you run, compute, message, cache your data, and also provides a machine learning interface. This is very important for us. Nagalakshmi will talk to you about it tomorrow. IoT Core, that's the brain of our IoT. It is that it's at that perception layer and transmission layer in between that. Let's connected device talk to each other easily, securely, and talk to the cloud also. Then There are other things, device management, device defender. I don't think these come as a part of free service, but core is very useful. You cannot build a single IoT application without core, without free RTOS. And then if you have very big applications, if you want to run some analytics, if you want to do site-wise IoT, if you want to handle events, all kinds of other complex things are there. And here is a little ad that Amazon puts. Morning we saw this iRobot, remember? iRobot microcontroller and things like that. So they use AWS IoT. They say LG Electronics uses, Bayer uses, Woodside uses, Volkswagen uses, and all. Imagine they use AWS IoT like we do, right? By creating an account and then go ahead and use it. So the basic thing is this, you have to sign into the console, create, and I'll let Nagalakshmi talk about it tomorrow. But I'll just give you one little, you know, sneak peek into it. So as I told you, you can have IIoT. You might have heard of this term, industrial IoT, right? You have these robots, these industries, all kinds of things, complicated ones. And there they have videos about how Volkswagen has used it to develop. And then they have use cases. You can use in this thing to do predictive quality, asset condition and monitoring, predictive maintenance. And these are the companies that have used. They have some case studies and what happens. You'll find architecture pictures like this. Similarly, if you go back, you can use industry IoT for AWS IoT for connected home. They again have some videos. You can use it for home automation, switch on and off lights, as I told you, open and close doors, manage the network of devices that you have through a Wi-Fi router. And all these are the companies that use for a smart home solution. And finally, they have commercial solutions, which are like smart cities. So what happens here? You need, of course, a lot of cloud and other things and all. They don't have use cases here because these deal with government and other things. But these are the various ways in which you can use AWS IoT to build applications. So I will stop here. Nagalakshmi will start with this tomorrow, giving you an introduction on what AWS IoT is and walking through to you through a live demo. She will log in to the console, tell you how to develop one small application, and maybe also give you an exercise that you could develop over the course of 1 week to learn about how AWS IoT works. So this is all that I had to share in terms of an overview. If there are any quick questions, I'll be happy to take.